Hello, good morning. Yes, students, how are you? Yes, hope all are you fine and safe at your home. In last session of free radicals, we have learned about the introduction of free radical, then some generations of free radicals. And in that generation, we have learned so many methods also. And today we will learn about the stability of free radical. Right? I think this is very important part of free radical content. So let's begin. I hope you all have seen the all last sessions and subscribe my channel as well, right? And enjoying the study. And also you are taking your notes, own notes you are going to prepare it. Right, so let's begin. Yes, is this visible well? Yes, great. Then this is free radicals in organic synthesis. Few methods, just we will revise it, which we have already learned about the in last session. This is Fenton reaction. There we have taken the starting material was the hydrogen peroxides, and using this metal, which is iron metal, it get converted into this OH radical, right? And what is the actually mechanism of that one is like this. So there will be extra electron, it will be add because of this metal. So means this Fe2 plus will get converted into Fe3 plus, right? So one electron it will release by this iron, and this OH will become OH minus, and another will prepare is OH radical, and this is our target free radical, or this is generation of free radical. The another peroxide which we have seen is tertiary butyl peroxide, and in this case also there will be formation of tertiary butyl oxide radical. So all the radical initiation pathways so far discussed given very reactive, short lived, okay, and which are useful in the synthesis. Another stable free radicals which we have learned, which is belongs to triphenyl methyl chloride. Okay, this was the starting material which we have seen, and this is the silver radical. There will be attack, and again the formation of triphenyl methyl radical, and we have discussed this one. This is quite stable because there are so many positions are there to resonance this radical. This radical will be uh, um, resonated by these all double bonds, and the position will get like this: phenyl group once, then another phenyl group, then third phenyl group. So there are a lot of positions you can find this radical, and again there are some chances that these two free radicals will get attached to each other, and there will be quenching type of nature. Quenching means you will not find in this structure, you will not find any free radical, right? Or these two molecule is also possible because of this radical and this radical get uh, make bond to each other, and there will be formation of this quench type of molecule, right? So this is the another method to generate the free radical. And now we'll start with the stability part. Also the thermodynamic stability is very important, and which these three are the free radicals which is quite stable. Out of that, one is DPPH, which is diphenylpicaryl hydrazine radical. So this is quite stable radical, right? Then another which is tempo, that tempo or TMIO, these two are also uh, quite stable free radical, right? And these radicals can be stored on the bench because of stability, right? Because other radicals are unstable. Okay, but this radical are stable, so we can store it on the bench and handle like other ordinary chemical without any adverse reaction in air or light. So please keep in mind that this TPPH, TEMPO, and TMIO, these are the quite stable molecules, right? Uh, then there are some chances no dimerization via nitroxide because all these belongs to the nitroxide ion, and you will get this alkoxyamine, and again this is stable. So identifying reactive radicals and studying radical reactions, you can find it here. And we'll talk little bit about the geometry of these radicals. See, normally configurational isomers are only obtained by breaking covalent bonds, and this is not the case with radicals. Because with radicals, bond rotation determines the geometry and hybridization of molecule. So this is the planar radical or AX3 type of radical. Like we can take example like CS3 also, right? CH3 radical. So is example of this AX3 radical, and which is planar. Sometimes it get converted in this side, so it will behave like pyramidal, and then um, if there will be some reaction, it will seem like tetrahedral type of molecule, right? Same way on this side. When it is in planar state, there will be hybridization, which is sp2 hybridization, and when it will become a tetrahedral, there will be sp3 hybridization, right? So this is the geometry about this radical. The another example is which radical having AX2 type. There also we can take some example like BeCl2, okay, and the radical. So in that radical also the shape is or geometry is sometimes which is linear, and it may converted into a non-linear format like H2O type of structure or geometry you can find it. And this geometry we can calculate or determine by ESR spectroscopy, and which is very useful to determine such features of the radical present in that. Okay, the next geometry is about the CH3 radical, SiH3. All are belongs to the this which group? This is 14 group elements, right? Carbon, silicon, germanium, and lead, and their hydrides. So CH3, SiH3, germanium hydride or lead hydride like that. So all are pyramid type of geometry. It all will show. And in that pyramid type of geometry, there are again two types. See, these two hydrogen are away from this X and H2, so there will be a staggered form. Okay, and when they are eclipse or overlapping to each other, right? So there will be another type of conformer, which is eclipse conformation. Okay, so this possibility is there. So as alkyl radicals become more substituted, so they become more pyramidal, right? Also when X is equal to SR, Cl, SiR3, GeR3 or SnR3, delocalization of the unpaired electrons into the carbon bond increases. The eclipse rotamer becomes the transition structure of rotation. In short, just keep in mind that these radicals can show pyramidal type of geometry. Okay. And now we'll start about the radical stability. As you know that in radical stability, there are two main types are there. One is thermodynamic stable radical, another is kinetic stable radical. Okay, is quantified in terms of the enthalpy of dissociation of RH into R radical and H radical, because what is the final product uh, become from the RH is either R radical or hydrogen radical. So the main factors which determine stability are conjugation, hyperconjugation, hybridization, and cathodic effects. Right. So one by one we will see. See, write down the carefully that in thermodynamic stability is depend on these four factors. One is conjugation, other is hyperconjugation, third is hybridization, and the fourth is cathodic effects. Right. So these four are the effects will majorly affects on the stability of the radicals. And how we can become it, we have already learned that this radical will become with this homolytic fission. Right. So first one is conjugation, and another name which is mesomerism. So this is the primary reason for the existence of stable radicals. Okay, the example is allylic radical, and see in allylic radical there will be a resonance. So because of resonance, and you know the rule of resonance, if some compound will give the more resonating structure means more stable. Okay, those same rule we have to apply here as well. So allylic radical will give us the two resonating structures. What about the benzylic radical? See, this is the benzylic radical structure, which is benzene having CH2 and the radical. So there are chances the first this radical will get converted into here, and next time will be here, and next time will be here, and again back to pavilion, right? And you will get this is the first. So almost 4 5 resonating structure will benzylic radical will show. So this is quite stable than the allylic radical. Okay, so this is the one method of stability which is conjugation, or another name is mesomerism. Great. Next one is hybridization. How hybridization affects on the stability of free radical. So first important quotation is for hybridization is pi radical is more stable than the sigma radical. Which one? The pi radical is more stable than the sigma radical. As the p character of a radical increases, so does its thermodynamic stabilization? Yes, sure. Because of in this vinyl or aryl radical, you can see carefully. These both radicals are in sp2 hybridization, or which is sigma radical. So cannot be resonance stabilized. Or if you can find this sp2 radical is there, then there will be no resonance. So which is unstable, you can say, or very reactive radicals. Understand? So pi radical is more stable than the sigma radical, and these two examples, both this vinyl and aryl, both are the sigma radicals, right? So understand, done? Yes. Next, the next example in that is the more stable, which is sp3 radical. It shows almost tetrahedron. Okay. And another example of pi radical is like this. See, we have benzaldehyde, and there will be a radical formation on here. Okay, so it will show some resonance structure, right, from here to here, and we can say which is pi radical anion. So a resonance stabilized ketyl radical. So this is more stable compared to the sp2 radical. The third method is which is hyperconjugation method. See, this is the radical present in the ethyl uh, compound, or we can say this is ethyl radical. There are chances of resonating structure. So many resonating structure we can draw it. See here, first this hydrogen get involved, then another hydrogen, then so there are 5 6 possibilities are there. Okay, out of this all possibilities, because of this all resonating possibilities, which is more stable radical, right? And if we have compared these radicals, here are the four uh, structures, which is one is methyl radical, one is ethyl radical, then this is propyl radical, and this is butyl radical, right? So you can see the clearly difference here, only two hydrogens here and no substituent. So total three hydrogens, which is methyl radical, is less stable because there are very few resonating structures. But what about here? So here there are chances of hyperconjugation. So because of three hyperconjugatable structures, which is stable compared to the methyl radical. What about here? Here are the chances is again more. These three will give the hyperconjugation structures, as well as these three hydrogen will also. And the same condition will here, rather than 3 6 here, it will give the 9 hyperconjugatable structures. Okay, so this the structure which is highly stable. Remember that the inductive and steric effects may also contribute to the relative stability of the radicals, means is also depend on the which group is attached here, right? So this is the third part, and the last part of the effect on stability on especially thermodynamic stability is the captodative effect, right? In that captodative effect, you can see the radical is attached on this double bond, having one electron withdrawing group and one electron donating group. So here, as a representative, the C is electron withdrawing group. I have shown it in red color, and this is electron donating group, which I shown in the blue color. Okay, so because of electron withdrawing group, this radical will get attached here or attack on here, and there will be formation of this radical. Okay, so here are some chances are there to attack. So if CHO or aldehyde group is there, then the stability is more. Then in nitro is almost the same. When is tertiary butyl type of group is little bit decrease, then methoxy again decrease, then ethyl methoxy again decrease, then amine and aldehyde again decrease, and so on. Okay, so the what type of group is attached there, whether which is electron donating or electron withdrawing, based on that the stability of radical you can find it, right? So because of this four method, we can determine the stability of, or especially the thermodynamic stability of the free radicals. So today we will stop here, and the next session we will learn about the kinetic stability and the stability factors affecting on the kinetic stability. Okay, so see you guys and the next session.